Okay, well, thank you everyone for attending today. This is Robert's completion seminar for his PhD. His PhD has been part of a linkage project with Toyota, and there's also a joint PhD program between the University of Melbourne and Birmingham. So he spent time during his PhD in Melbourne, the UK, and Japan. So he's been all over the world. The PhD topic itself is really about starting to use new optimization techniques for MPC tuning. And I'll let him explain these in a bit of detail and some of the results he's been able to obtain over the past 3 and a bit years. So I'll hand over to Robert now to get on with the technical part of the seminar. Thanks, Robert.
Yep, thanks for the introduction, Chris. So just a quick outline of today's presentation. So after the introduction, we'll give a brief mention of some of the other contributions during the PhD. But the main focus of today's talk is going to be about sequential learning algorithm for controller tuning. So we're talking about controller tuning. Sorry. Let me just double check I've got the right version of the slides. Okay, yeah, for some reason, the version I had there was missed out a few slides, but we're good to go. So we're talking about controller tuning. And so if we think of manual controller tuning, we've got this human calibrator here. And what they might do in manual controller tuning is they have a controller parameterized by theta here. They go and test that on some plant. They obtain a closed loop trajectory. And then they look at the response of that and then decide to update the parameters of the controller based on the characteristics of the trajectory. So suppose this human calibrator would rather not have to do so much manual tuning. And so the natural thing to do would be to offload some of this work to a computer. So now we're considering an automated controller tuning approach offline. So now we've got a model of the plant and a controller in simulation. So this generates a closed loop simulation, which gets evaluated through some performance index in conjunction with some optimizer that's going to update the parameters of the controller. But what this human calibrator is thinking is how they can get this offline tuning to actually replicate the preferences of how they would tune it if they were manually tuning it. So it's actually not that easy to obtain and write down a function that describes human preferences. So this is where machine learning can come in, which is consider this approach where we ask the human calibrator to rate a couple of responses, and then they so they provide like some numerical rating, and then this consists of a data set that we then learn a mapping from, say, for example, the time domain features of our trajectory to a preference rating, and then this gets used as our performance index. And so this was actually done in some previous work where this was appeared in a conference paper where we applied this concept using machine learning to learn some preferences to tuning MPC for the diesel air path. So yeah, this is in collaboration with Toyota Japan. So we asked a Toyota engineer to rate a few trajectories, and then this was used to learn a preference function, which could then be used to tune the parameters of MPC. And the tuning parameters we're considering here are the QPR matrices of quadratic cost function in MPC. So this kind of automated tuning approach is very much suited for MPC, because if you think about the relationship between the elements of these QPR matrices and the closed loop response, that is not a trivial relationship. So it would help if we can offload some of this effort to an automated approach, and it would save on what would otherwise be a very time-consuming and a very non-intuitive manual tuning procedure. So once we've got a tuned controller offline, then logically we want to then go ahead and test it on the physical engine. And so actually at the Toyota facility in Japan, they don't allow you to take in cameras. So unfortunately, I don't have a picture of the diesel engine plant, but I have this drawing instead. So an ordinal optimization approach, and I'll talk more about ordinal optimization later, but an ordinal optimization approach to offline tuning would be to first get some candidate controllers, which could have come from our framework here. We get a few candidate controllers, and then ordinal optimization says, well, we select the best of these to test on the physical plant. So we select this theta star here, the best controller we saw offline, and then we implement that on the engine controller unit to test. So a question that can be asked here is, well, can this tuned controller, can the performance of that be robust to the inevitable plant uncertainty? So in other words, if you observe some good performance offline, is that going to be indicative of good online performance? And so now I'll come up with a few motivating examples for why I want to consider a question of this type. So in the automotive industry, so you're never going to have an unlimited amount of time to do your controller testing. So yeah, you usually have some limited budget to perform controller testing or tuning on the physical plant. And this is especially true in our experience, where we have maybe 1 week booked in Japan to do testing, but we have a few weeks or months before that in advance where we can perform some offline tuning through simulation. So it makes sense to want to make use of that offline tuning time to tune some controllers to then take on to the physical plant to test it when we get to Japan. And so there was some work on this project which was presented at IFAC last year, which successfully demonstrated some algorithms for online MPC tuning. So then the research that I'm proposing here, offline tuning, this is actually complementary to the online tuning procedure, because what it says, if we can somehow say we have these good offline tuned controllers, then we can use them as good initial points for an online tuning procedure. So the second of the motivating examples is, say we've got a tuned controller that we're going to then deploy over a fleet of vehicles. And there's going to be some variation in the plant dynamics of each vehicle, but we're deploying the same controller on all of them. So maybe we can also say something about how robust is this single tuned controller going to be across all the plant variations in the fleet of vehicles. And so the research that's being proposed here can address both of these situations. Okay, so I'll take a quick detour to talk about some of the other contributions which still relate to the tuning framework, and they appear as chapters within my thesis. So the first, I'm sorry, I think there's been a mix-up with the slides when I downloaded them, but this is where we should be at. This first chapter is related to this part of the framework. So the part related to the performance index. So yeah, this piece of work here proposes the following thing. So first of all, instead of having numerical trajectory ratings from our expert, let's suppose we have pairwise comparisons. So to collect our data, we've asked the expert to provide a rating. So we ask them, given these two trajectories, which one do you prefer? Do you prefer A or B? And then the expert says whether they prefer either out of A or B. And they do that for many different pairs. And that consists of our data set, which we're trying to learn preferences from. The second thing is that we have some monotonicity constraints on particular features. And the reason for why I want to do this, to give an example, is we might have some knowledge that some features are more desirable than others. Say, settling time, I guess it's very reasonable to say that if we have faster settling time in a response, then that's better, given that all other features are unchanged. And so trying to have this shape constraint in regression, this is called isotonic regression, but not the sports drink kind. And so we want to enforce these monotonicity constraints on our learned preference function. So each of these has been quite extensively studied separately, but in our proposed approach, we look at the two together. So we propose an approach which performs isotonic preference learning using pairwise comparisons. And we do this using Gaussian process regression. And this research was presented at CDC a couple of years ago. The second chapter relates to this part of the framework, the system identification of this model that you're using in offline tuning. So first of all, the dynamics of the diesel air path is actually quite suitable to be modeled with an LPV model because you can parameterize the dynamics in the engine operating point. So we can use an LPV model for the diesel air path. And as before, we want to be able to, we have a limited amount of time to conduct physical experiments. So we want to identify a model by conducting as few experiments as possible. And so the approach proposed here is using active learning. So again, with Gaussian process regression, we can query this Gaussian process to see which operating point is there currently the most uncertainty, and then conduct the next experiment locally at that operating point, and then add that to our LPV model and sort of try to fill in all the gaps. And an additional utility to this is that we can probabilistically quantify the plant uncertainty this way. Okay, so now moving on to the main course of the talk today. So we're going to be discussing this algorithm for controller tuning. And to provide a bit of notation and definitions. So first of all, we've got some controller parameter theta, which comes from some set. And we've got some mechanism that allows us to draw candidate controllers from some distribution. So for example, it could be from this framework here, where we inject a bit of randomness into the optimizer to give us some random candidate controllers. Secondly, we've got a plant parameter psi, also from some set, and we've also gone and quantified the uncertainty of the plant model via this distribution here. So we'll define the controller performance function as a function which allows us to compare any two controllers. And another function called the system performance function, which is now actually in terms of your plant as well. So given a plant and a controller, this then evaluates the performance of that controller theta with that plant psi. And if we make the additional technical requirement that these functions are measurable, then this is going to induce a joint distribution over these performances. And so moving on to now the assumptions of our algorithm. First of all, we're given some performance specification J star, which we want to meet on an online test. And so the goal here is to actually use our algorithm to tune a controller offline so that when we go to test this tuned controller offline or online using an independently realized plant, then we're going to meet this performance specification J star with high probability. And so to list the assumptions, the standing assumptions for our algorithm. So first of all, this induced joint distribution here. So this distribution is not fully known. However, we do know that it is a continuous distribution and it also has some positive dependence. And I will be a bit more precise about what this positive dependence means later on. Secondly, the copula of this joint distribution, and so I haven't defined what a copula is yet, but for now it is enough to understand that a copula is a property of this distribution. So the copula of this distribution is not too far from the associated Gaussian copula, which can be quantified with some value nu. Okay, so thirdly, this performance specification here, J star, this is feasible, and what that means, roughly speaking, is that if we draw a candidate controller randomly, then there's a non-zero chance that it's going to meet our performance specification. And the last assumption here is, so we don't know this distribution fully, but we are still allowed to sample from this distribution. And we do that by drawing samples from our controller and plant distributions and then going to evaluate them on our performance functions. So I can now give you a flowchart of what the algorithm looks like. And so at the moment, some parts of this algorithm might seem opaque because I haven't provided all the details yet. But the main things are you've got these algorithm settings, beta 1, beta 2, and delta. And so this algorithm is going to sequentially draw samples from our distribution. So it draws a sample of a controller plant pair, evaluates that to get a sample of performances. And then so we're going to accumulate a sample, and from this sample we can compute some lower confidence bounds. And from this lower confidence bound, we can then check this condition, which is if this so-called success probability lower confidence band, whether this is greater than or equal to some threshold. And if it isn't, we keep drawing more samples. But if it is, then we stop the algorithm and then we return the best performing controller throughout the algorithm run. So I can now give you the main result of this algorithm, which says, well, under the assumptions stated on the previous slide, if we choose our algorithm settings in this particular way. So given some gamma, then we choose our algorithm settings in this way. Then with high probability, greater than 1 minus gamma, the performance of your tuned controller from the algorithm when tested on a realized plan is going to meet your performance specification. And so in terms of the rough idea behind the proof of this result, first of all, we can just write this, this probability here as the probability of a successful test. And then we'll introduce this auxiliary event calligraphic A, which we can then factor out into two probabilities. And then it can be shown that this conditional probability is lower bounded by 1 minus delta minus nu, while this probability of this auxiliary event calligraphic A is lower bounded by 1 minus beta 1 minus beta 2. And so it then follows under the choice of algorithm settings here that this probability of a successful test is going to be greater than 1 minus gamma. And so in the next couple of minutes, I'm going to go through and try to develop the parts of this proof sketch. So where these lower bounds here, where these are obtained from, and what kind of tools are used in obtaining this result. So yeah, one of the main, another area of contribution throughout the thesis was in ordinal optimization, and in particular some lower bounds in ordinal optimization. And so now is a good opportunity for me to quickly remark on ordinal optimization and randomized algorithms, which this algorithm draws a lot from and is inspired a lot by. So ordinal optimization and randomized algorithms are both from areas of the control literature, and they're both are to do with trying to find approximate solutions to difficult design or tuning problems under uncertainty. And so for ordinal optimization, this was introduced in the discrete event dynamic systems literature, one of the pioneers being Larry Ho from Harvard. And the randomized algorithms, this came about in the probabilistic robust control literature. And the pioneers here, among others, being Vidyaska and Roberto Tempo. And so even though the results from these two areas are quite different, they both share a similar philosophy, which says, well, there's actually a way to justify the practice of simulating many random designs and then picking the best amongst them. And another similarity shared is that they have some notion of goal softening, in which we can use this to control the degree of suboptimality of your approximate solution. So to be able to properly introduce what ordinal optimization is and the resulting bounds that were developed, I will now give you this thought experiment, and it's framed in this job hiring context. So suppose I've got 100 job candidates for a position, and each candidate has their quality drawn from some standard Gaussian population. So we're the hiring manager here. So we're going to interview each candidate, but since interviewing is a noisy process, we're not going to observe their actual quality, but instead we'll observe their quality perturbed with another standard Gaussian perturbation. And so what we do, and the only thing we can do, is to select the candidates for the position based on their observed quality. So let's say we hire the best 5 observed candidates. And so the question here is, of the selected 5 candidates, what is the probability that at least one of them is a top 5% of the population. In other words, they're an actual good candidate. And so the first time I saw this, the answer was quite unintuitive to me. So the answer is actually really quite close to 90%. And it feels unintuitive to me because, well, you've essentially got a noise to signal ratio here of 1. You're adding noise of the same variance as the original quality. But I guess this sort of experiment does demonstrate in some way where this ordinal optimization approach of selecting the best can be somewhat robust to noise. So we can go ahead and replace all the words here with something a bit more relevant to our canonical controller tuning example. So now, instead of interviewing each candidate, you're simulating each controller. So in a way, if you're simulating a controller, it's as if you're interviewing that controller and seeing if it's any good for the job. And then we're going to test these controllers and seeing if they are actually good for the job. And we're asking, well, what is the chance that at least one of them is good? So taking this thought experiment, we can formalize the problem a bit. So now let's suppose we've got this IID sample of size n of these observations, which we'll call Z. And this consists of some X value, which is the thing we care about, plus some noise Y. And Y has some variance of Xi squared. So we'll go ahead and observe all n, and we'll select the best m, denoted like this. And each of these observations is decomposed into its original X that we care about and the noise. And so we ask, well, the success probability is the probability that at least one of these X values that we care about is less than or equal to some threshold, where this threshold is defined by the 100 times alpha percentile of the distribution of X. So there's a few key observations here we can make about this success probability. First of all, we can actually just consider the joint distribution of Z and X. So we don't actually need to specify what Y is if we're given this joint distribution. And also, if we transform the distributions of Z and X by some strictly increasing function, then the success probability is going to be unchanged. And this, in a way, gets you to see why this is called ordinal optimization, because the ordering here, if you transform the Z, this ordering will stay the same. So we're still going to select the same candidates. And also, if you transform X, then this percentile value here will also change accordingly so that the success probability is unchanged. So then we can generalize the problem statement and say, well, now X and Z can belong to the class of continuous distributions where we can transform a bivariate Gaussian by some strictly increasing function. And this can be characterized with a so-called bivariate Gaussian copula. So Z and X don't need to be jointly Gaussian before, as we considered earlier, but now they can just come from this class of distributions. So here I'll introduce what a copula is and just provide the relevant background. In simplest terms, a copula is a multivariate distribution with uniform 0-1 marginals. And so we can represent any distribution just in terms of its marginal distributions and a copula. So to illustrate this, suppose we want to sample from a bivariate distribution. Well, to do that, we can first sample from its copula, and we get this pair of uniform random variables with some dependence between the two. But then we can use the inverse CDF to generate the marginals with that dependent structure still within there. And so there's a result called Sklar's theorem, which says, well, for continuous distributions, the choice of copula in this representation is unique. So then to define a Gaussian copula, if we have this joint Gaussian here with standard Gaussian marginals and some correlation rho, we can define the bivariate Gaussian copula as the distribution of this here, where phi is your standard Gaussian CDF. And this here is just an illustration of what the copula density looks like for different values of your correlation. So now rephrasing a success probability, we can say that this joint distribution ZX has a continuous distribution with a bivariate Gaussian copula and positive correlation. And as before, we select the best M out of N. So we select Z, but each of these is associated with some hidden X value that we care about. And then we analogously define the success probability as before. But now this one is in terms of the correlation rho. And there's actually a way to make this equivalent to the problem from before, which is by relating the correlation rho to the variance psi squared via this relationship here. So I can say a few things about this success probability. So first of all, we have this non-decreasing property in each of its arguments. We also have this high probability property, which says, well, we can find an n, a sample size n big enough so that this success probability is at least 1 minus delta. And so this really also says that we have this convergence property where if we take the sample size to infinity, our success probability is actually going to converge to 1. And if we want, we can also evaluate this success probability by computing an m-dimensional integral, but rather than numerical integration, we have this analytic lower bound for success probability. So first of all, given some angle omega and defining these variables via these recursive relationships, we can say that this expression here is going to lower bound the success probability for all values of n greater than some n star, which depends on your value of omega. And what can also be done is, so given the value of n, and for a particular omega, you can actually verify whether it's safe to use this analytic lower bound, which then means we can do a sweep over omega and obtain this optimized bound for the success probability. And to illustrate this analytic lower bound, using a few plots here. So in this first plot here, we've got the shape of the lower bound quite closely resembling the shape of the curve if you do this using numerical integration. However, if you actually try using a numerical integration for higher values of n, it's not going to work out quite so well because the integrand gets a bit extreme for larger values of n, so you'll find that it won't give you accurate answers, whereas the analytic lower bound doesn't have an issue with that. So we can keep going with higher orders of magnitude and computing it for larger values of n. And this plot here also illustrates that the lower bound itself does have that convergence to 1. In the plot down here, this also just gives you the resemblance of the shape, but also the monotonicity properties in both your correlation rho and your alpha parameter. Another thing we can do with this lower bound is invert it. And what I mean by that is, suppose we're given all the other values and we want to find a value of the sample size n bar such that for all n greater than or equal to n bar, the success probability is at least 1 minus delta. So it's some high probability. And so we can do this using this form of lower bound. And to give an example, say we want a high probability of at least 99%. So this says we can find, well, n bar is around 16,700. If we get our sample size to be at least this big, then the success probability is going to be at least 0.99. in a more extreme example, if you make the correlation really, really small, then it will give you this value for n bar, this crazy galactic order of magnitude value for n bar. And if you make your sample size this big, then your success probability is going to be at least 0.99. But I think, yeah, it's the fact that we can do this at all with this analytical form of the lower bound. Whereas if you tried to find this value using numerical integration, I don't think you'd have much success. So we can now move on, and apart from the Gaussian copula case, and now consider, well, what if Z and X has a non-Gaussian copula? And so without loss of generality, we can assume that Z and X is a copula distribution. So Z and X is some general non-Gaussian copula, but it still has some positive dependence property to it. We can define our success probability analogously for this non-Gaussian copula. And we can also obtain a few properties, and some of these are similar to before. So we can still compute this using an m-dimensional integral. We've also got this monotonicity property. We can also come up with some general upper and lower bounds for this success probability. But sadly, we don't have this property in general, where if you make the sample size go to infinity, the success probability converges to 1. So I can give you an example of a copula where the limit of this will not be equal to 1. However, we can still come up with a lower bound on the success probability by relating it to our results from the Gaussian copula. So now here, to be more precise about this positive dependence condition I've talked about. So let's say our arbitrary copula has a positive Kendall correlation defined by this expectation here. So it's got a positive Kendall correlation. So then we can define the associated Gaussian copula for this arbitrary copula as the Gaussian copula with the same Kendall correlation, which has rho equal to this relationship here. Then if we give the condition that your arbitrary copula is not too far from its associated Gaussian copula via this upper bound here, nu, then we can say, well, the success probability of this arbitrary copula is lower bounded by the success probability with the associated Gaussian copula, and also this value of nu. And so taking all the results so far, we can bring this back into the context of controller tuning. So now let's suppose we're drawing NID controller candidates from our distribution. So for example, we can use our framework here as our mechanism. We have randomness in the optimizer to randomly draw some candidate controllers. And we say our tuning controller is the best offline performer. So then when we go ahead and try to test this, so we independently realize a plant from our plant uncertainty distribution and test it online with our offline tune controller. If we then make the distribution of our performances equal in law to some arbitrary continuous distribution with some copula, then we can actually relate the probability of a successful test to the non-Gaussian copula ordinal optimization success probability, with alpha being defined by this relationship here. So we can't apply that straight away because we're not given the distribution of this, but we can draw samples. So we're actually going to need to estimate the value of alpha and also the value of rho of the associated Gaussian copula. So if we've drawn a ID sample of size n from this distribution, then we can come up with some finite sample lower confidence bounds for alpha and rho. And this can be derived using some concentration inequalities, mainly the Hoffinger inequality. But yeah, we can compute this alpha hat underline from our sample and say that with high confidence, at least 1 minus beta 1, the actual value of alpha is going to be greater than the lower confidence bound we compute, and respectively for rho. So applying these lower confidence bounds, we can actually come up with a lower confidence bound for the success probability. So with high confidence, at least 1 minus beta 1 minus beta 2, the non-Gaussian copula success probability is at least this value, which is from the analytical lower bound in terms of your lower confidence bounds for alpha and rho, minus the value of nu that we assume. And so then going back to this algorithm again, this condition here that we check, this success probability lower confidence bound is actually the Gaussian copula success probability lower confidence bound that we can evaluate from our lower confidence bounds that we compute from our sample. So we check if this is at least 1 minus delta. So what's not immediately clear is whether this algorithm is guaranteed to stop in a finite time. Because if it does stop, then it returns this success probability at least 1 minus delta. But whether it does stop or not is another question itself. And the answer to that is affirmative. So if we consider the number of samples that we draw as a random variable tau, then we can show that we've got this lower bound here for the distribution of when it stops. And we can compute this bound a bit more precisely, and this can be useful for giving a not too shabby prediction of when our algorithm is going to stop. So in this example, it's within 1 order of magnitude compared to a simulation of the algorithm. But the key takeaway here is that we can show that our stopping time tau is almost surely finite. So we're going to stop when this lower confidence bound for the success probability for the Gaussian copula case is at least 1 minus delta. And so now we can paint a clearer picture of how this all fits together into the main result of the algorithm, which is when you factor out your probability of successful test here, well, this probability of this auxiliary event A is lower bounded by 1 minus beta 1 minus beta 2, which is actually the confidence level of this success probability for the the lower confidence band for this success probability, while this term here is lower bounded by the actual value of the lower confidence bound here. So you have a 1 minus delta here minus this nu term. And then this gives you the 1 minus gamma under the particular choice of algorithm settings. So let's go and take this to a numerical example. And so since we're considering diesel air path control with MPC, we've got this MIMO control problem here. We've got 3 inputs and 2 outputs. And since we've got some state and input constraints, we can address this using MPC. Our controller distribution for generating candidate controllers, our plant uncertainty distribution here, this came from the active learning approach mentioned earlier. So we obtain our plant uncertainty from this active learning approach, while the distribution for generating candidate controllers, since the MPC matrices are positive definite matrices, we can construct a distribution to generate a random positive definite matrix based on spectral decomposition using an approach very similar to the one in the proposed machine learning tuning framework in that paper. So here we'll make the performance specification for simplicity to be 6.5 seconds settling time for one of the outputs, and then we'll evaluate each of our controllers in an offline setting using the nominal model in a closed loop. So after one run of this algorithm, it stopped after drawing 37,000 samples, and this is just a histogram of your performances from your samples. And so this is a simulation study, but if we pretended to go and test this single tune controller from the algorithm on a fleet of 10,000 vehicles with varying plant dynamics. So we test each of these 10,000. For this algorithm run, actually all 10,000 tests met the performance specification. And it seemed to actually exceed quite a lot the performance specification. So the highest settling time amongst all 10,000 tests was 5.1. And also the proportion of successful tests was 1, which was much greater than the expected proportion, which is guaranteed by the algorithm, which was 0.7. And we saw similar results for multiple algorithm runs. So it seems like there could be a bit of conservativeness in the guarantee provided by this algorithm. And in terms of where I think this conservativeness is coming from, so some could be inherent from using lower confidence bounds, but I think in this example, the actual copula could be more favorable to the success probability than its associated Gaussian and being reflected by the new parameter. So now just to summarize, if you're interested in further details, you can find the preprint on arXiv, but what this presentation today mainly considered was the offline tuning of controllers by simulation, and then being tested online subject to some plant uncertainty. We proposed a sequential learning algorithm which was able to guarantee that a performance specification was met with high probability, and also that we applied this on a numerical example with MPC for the diesel air path, and it was successfully demonstrated to be able to tune a controller for a fleet of vehicles meeting the performance specification. So in terms of some future work, well, some of these results were obtained towards the tail end of last year, so we haven't had an opportunity to go and combine this offline tuning approach and complement it with online tuning, so that could be done in the future. We also just looked at doing this for MPC, so we could try applying this to some other classes of controllers. Another interesting thing is whether there's some way of designing this mechanism for generating candidate controllers to be more favorable to the success probability. And for the analytic lower bound for ordinal optimization, so currently it's valid for all M, but if you increase M, the lower bound doesn't improve with it. So it'd be an interesting direction to see if there could be an analytic lower bound that does improve when you increase your selection size M. And lastly, it'd be interesting to see what happens if we relax the assumption that the distribution of your performances is a continuous distribution. Okay, so that concludes my presentation. I hope you enjoyed it, and thank you for coming.
Thanks, Rob. Do we have any questions for Robert?
I've got a question.
Yep.
Hey, Robert. Thanks for the talk. So you had two different cost functions. You had J bar, which is for the controller, and J, which is for the whole system.
Yeah.
I'm just wondering why. So what can you do with the two cost functions, what can you do with J bar that you can't do with just J? So yeah, what additional flexibility, like why can't all your desirable features just be encoded directly in the system performance function?
So the system performance function also has your plant as an argument, which then if you're trying to compare two controllers, then it's not enough just to give the control, you also have to give a plant as well. So one way to think about this is, well, if we just fix the plant to some nominal value, then we could get a control performance function which just allows us to purely compare two controllers.
Yep, I see. All right. Okay, and then how? So, is there some way of just? Are you saying could you just integrate out the plant in some way?
Yeah, if you could like take the expectation over this, assuming
Yeah.
that's possible, yeah, you can choose that. Yeah.
Okay, so that's how to think. All right, cool. Thanks. That makes sense.
Any other questions?
Yeah, Man, I'll ask a question.
Sure. Yep.
Thanks, Robert. That's interesting stuff. I'm just a little bit stuck on something you brought up in your future work slide, which I was actually thinking about for the whole talk, and that was the role of a distribution on the controller parameters. Given that that's something that's you're choosing, right? So can you describe a situation which you wouldn't be taking just a uniform distribution over a sort of bounded region of the parameter space?
So yeah, that does relate to this future direction, which is at the moment I think the understanding is really not quite there why you might choose this distribution and it might lead to a better success probability than another. What I can say, however, is in the end it does come down to the underlying correlation between these two controller performances. So if you can design a mechanism in such a way where a good performance in simulation will predict some good performance when you test it on the plant, then that's really the thing that underpins your success probability. And so choosing a uniform distribution that could be done, and whether or not that leads to a better success probability would have to, I would say, it depends on a case-by-case basis, whether that, because
so is it equivalent to think, so if you're thinking about J bar as perhaps a measure of control performance for a nominal model of the plant, could you translate this into a question of how to choose that nominal model of the plant to help as well in some way in terms of the probability of success? Is that impacting the way you choose J bar, and is that related to the same question about how to put a distribution on theta?
So what definitely feels intuitive is, well, you want to choose your nominal plant, which, as much as possible closely resembles the actual plant in some sense. So maybe the expectation of your actual plant, or the expectation taken over your actual plant. So yeah, what I mean to say is that, well, intuitively, if you perform good system identification and you can get a good enough plant, then that is going to give you a good enough correlation between these two, then that will give you what you want.
All right, thanks. So it seems like the two things are related, would be related, the questions.
Yeah.
Okay, all right, thanks.
Okay, thanks, Michael. Any other questions?
I had a question.
Yeah.
Can you say something about the relationship with this approach and the scenario approach? And is there any clear connection between them? Thank you.
Yep. So the scenario approach, and you can correct me if I'm wrong, but so I believe the plant here is from a finite set. Is that correct?
Basically, you have a few parameters and maybe some realizations.
Yeah. So you're comparing it just for a few finite number of realizations from the plant. So it is in many regards similar to the scenario approach, and the scenario approach does come up in the randomized algorithms literature, which this algorithm here is based a lot upon. If you're asking for more, say, theoretical relationships, I haven't looked into that. But yeah, I can definitely see some connection between the two.
All right, thank you.
Thanks, Amir. Any other questions? We have time for one short question. Otherwise, we can thank Robert for his talk.
I've got one short one.
Sure.
Yeah, Robert. So if I understood you correctly, you're relying on the user to give you J bar for a given theta. Is that correct? So someone rates
Yeah, so that could be an example of a J bar. It's not that restrictive, it's more general than that. So an example of a J bar could be obtained from machine learning.
Yeah.
But in the numerical example I showed, the J bar was just the settling time in the nominal with the nominal model in closed loop.
Okay, but isn't that given also a particular parameter, plant parameter value? Like, isn't that given a particular psi? So how do you how do you remove the dependence on psi?
So the dependence is removed by saying this is the nominal model, which is used in the MPC predictions. Yeah.
So they're not looking at an actual plant, they're looking at a simulation.
Yeah.
Okay.
Okay.
Cool.
Cool. Thanks a lot. If anyone has any more questions, please contact Robert. And thanks again, Robert, for your talk.
Yep. Thank you.